Good afternoon. Welcome everybody. President ISVS Dr. Simrat Sagar Singh and myself, Executive Secretary ISVS, welcome all the attendees for this webinar. Dr. M. Raghunath is deft in handling orthopedic cases. His skill sets are refined and updated for handling both large and small animal orthopedic cases. His experience at Gadwasu, Ludhiana and Sri Venkateshwara Veterinary University, Tirupati will help attendees to internalize the concepts and make the orthopedic learning curve less steep. Now I request Dr. Deepak Tiwari, Treasurer ISVS, for a brief introduction of Dr. M. Raghunath. Dr. Tiwari, please.
Thank you, sir. Good afternoon to all. Dr. M. Raghunath is working as a professor of surgery in the Department of Veterinary Clinical Complex, College of Veterinary Sciences, Sri Venkateshwara Veterinary University, Tirupati. He did his BVSc and AH from Acharya N.G. Ranga Agricultural University, Hyderabad in 1997 and subsequently MVSc in Veterinary Surgery and Radiology from the same university in 1999 and PhD from Punjab Agricultural University, Ludhiana in 2000. He has academic experience of 18 years, guided 17 MVSc and 1 PhD student as major advisor and member of advisory committee of 43 postgraduate students. Dr. Raghunath acted as principal investigator for 2 and co-PI for 3 externally funded research projects. He has published more than 110 research and clinical articles and scientific journals of national and international. He has presented 160 papers in various international and national congress or symposia, delivered 45 invited lectures in various seminars and trainings, and published about 10 extension articles. He was bestowed with 23 national awards, including gold medals and appreciations for best research papers in various international and national level scientific symposia and conferences. His thrust areas of research includes design and intermedullary interlocking nailing system for small and large animal fracture repair for the first time in India, fracture repair in large and small animals, bone grafting, joint surgeries, canine memory neoplasm, 4 stomach disorders, and urinary affections in large animals. Thus, looking into his considerable experience of Dr. Raghunath in the field of veterinary orthopedics, I request him to deliver today's webinar on evolution of plating procedures for repair of canine long bone fractures. Dr. Raghunath, sir, please.
Thank you. Good afternoon, everyone and all the delegates who have registered for this webinar. And the topic what I am going to present today is evolution of plating procedures for repair of canine long bone fractures. So why we have so much of choice in choosing an implant, particularly if you talk about bone plating. And why these implants have developed, why so much of choice for an orthopedic surgeon, and what is the necessity for the evolution of these different plating procedures that are available today for a veterinary orthopedician. So this is briefly what the background of the present topic, and we will see how the changes in the concept of bone healing because of advancement of imaging procedures, imaging technology, advancement in Doppler studies, and advancement in biomechanical studies that have happened in vitro and ex vivo studies have changed enormously the concept of bone healing from what it was in some 30-40 years ago and what it is today. And that is a necessity basically why the latest procedures have been adapted or developed. Few are adapted from human orthopedics and few are developed exclusively for veterinary orthopedics. And this is the basic background. And the objectives of the present seminar or webinar is to understand how changes in the design of plates have evolved according to the change in the concepts of bone healing. So this is the basic objective of today's webinar, and how the changes in concepts of bone healing. We know that in earlier stages the concept of bone healing was entirely different from what we are following or what we are preached and what we are telling to our students. So that is the reason why the evolvement or evolution of the plating procedures has happened. And to understand how we can use a plate in several different ways to achieve different types of fixation. So the same type of plate, how it can be used in different circumstances. And we will try to see certain case studies here, which we have done at different places in my career. And when we try to take up the challenges for an orthopedician, so we try to take each challenge at a different aspects of presentation, and we will try to see how the present day changes in plate design have counteracted those challenges that are encountered by an orthopedician. So this is a basic background of basic biomechanics. What are the forces that act on a bone? This we all know. So there are certain 5 different types of forces which act on a bone, leading to the loss of elasticity of the bone. And at one stage where the bone will show a fatigue place and it will undergo a deformation. That's what we call it as a fracture. So different forces like bending, torsional, axial compression, axial tension, and shearing forces. Bending is when it bends on a longitudinal axis. Torsional are always circular motions, which when the bone twists on its longitudinal axis, that is a fracture. And compression is when an animal lands from a height on a ground, and the equal and opposite reaction. The one reaction is when it lands on the ground. The opposite reaction is when the gravitation, because of gravity, when it lands, and the opposite ground forces will cause compression at the one side, and it will lead to second fracture. And axial tension is when there is a equal and opposite reaction on the bone. One reaction is when it's own weight of the animal when it lands on the ground. And the opposite is the muscle pull. When the muscle pull hardens in an opposite direction, that is tension. And shearing is when it slides over its axis, resulting. So majority of the cases which we encounter, they are usually will be the combination of either 1, 2, or 3 forces, and that is how the fracture is present. Coming to the implantology, the basics of the implants that we usually use. So first we start with the type of screws, which are very, very essential to have an idea on the screws when we talk about plating, because it is a screw that holds the plate with the bone. So usually we operate with 3 different types of screws, depending upon the area of the bone and the function of the screw. So area of the bone, we classify them as cortical screw and cancellous screw. And the function is when we have a specialized screws called locking head screws when you want to lock the screw with the plate. So these are different types of screws. And as the name indicates, cortical screws are those which are used in compact or hard bone. We know that the bone is divided into the extremities are always spongy, the cancellous bones, and the diaphysis is always cortical, where you have 2 cortices that are to be crossed by the screw and crossing through the medullary canal. So these are the cortical screws, are those which can be used in the cortex area, cortical area of the bone, and they are usually made up of 316L low carbide alloy of stainless steel, and they are available from 1.5 mm to 6.5 mm depending upon the diameter of the bone or diameter of the diaphysis. And cancellous bones are those which are used in a cancellous part of the bone. They are available as a partial threaded and also a full threaded, like a cortical bone, which you have seen earlier. And they are fully threaded screws are also mainly used for metaphyseal and epiphyseal areas, where, as I said, the bone will be very spongy, loose bone. And the purpose of these cancellous is the thread of the cancellous they have more thread, and the purchase of the screw with the bone will be more when compared to the purchase of a cortical screw. So because we are working on a cancellous area and you want to use the screw on a cancellous area, the purchase, the holding capacity should be more than a cortical screw. So that is the reason why the pitch of the screw will be more when compared. So now if you want to differentiate for an orthopedician when you are working you should be in a position to, just by holding the screw and just by looking at the screw, you should be in a position to identify the screw what you are using. Because you should not use a cortical screw in a cancellous area, and vice versa should not happen. So to differentiate, just by holding a screw, you should be in a position to tell whether it is a cortical or a cancellous. The basic difference, if you take between these screws, is the unit length of a screw. Suppose you take a unit length of a screw, the number of threads in a cortical screw are more, whereas for a unit length of the screw, suppose you take a 3 mm unit length, the number of threads in a cancellous screw are less. So this is the one basic difference. The second difference is the core diameter. The core diameter of the cortical screw is more, whereas the core diameter of a cancellous screw is less. So this is what we call core diameter, is other than the pitch. So the base diameter. So this core diameter in cortical is more, whereas core diameter of a cancellous is less, and the pitch height is more in a cancellous and it is less in the cortical. So when it gets driven in the bone, so this much space of the screw will engage the bone, and because it is working in a cancellous area, it will have more purchase, whereas only this part of the screw will engage the bone, and because it is a hard bone, cortical bone, so this is sufficient when you are working in a cortical area. And they are available as both cancellous. The cancellous are available both as partially or fully threaded screws. So locking head screws are the further advancement in the, when we take up different types of plates, we encounter these type of screws, specially used for certain type of specialized plates, where the head of the screw, you see this, so the other part of the screw is now similar to the normal cortical and cancellous. Even in locking head, you get a cortical. In locking head, you get a cancellous screw. Some are self-tapping. Self-tapping are those which, after drilling a hole in the bone, without the help of a tap step, we can directly introduce the screw. Whereas some screws will come with a normal end where we have to tap the hole. So this is the magnification of the head of the screw, where the magnified area is showing that the head of the screw is also having threads. So these threads are basically the difference between a normal screw and a locking head screw, and these threads will go and engage the threads of the plate, which we will subsequently be seeing. Now, where these bone screws are used, where, in what circumstances and in what areas we use these bone screws. One is to provide interfragmental compression using the lat screw principle. So this is when we are using a screw as a fixation option, when there is a wedge shaped fragment in the comminuted fracture, or if it is a very long oblique or a spiral fracture, to create interfragmental. Interfragmental is between one major fragment and another major fragment. If you want to create a compression across the fracture line, crossing the fracture line, we can use this screw as a lat screw, or the same screw can be used as a position. Position screw is, suppose there is a chip in the bone, you want to hold that chip along with the primary implant. So this can be used as a positional screw, and normally as a plate screw. Plate screw means through the plate when we apply on the bone. So one thing we have to remember, when you are applying a screw as a plate screw, the screw as a plate screw should never cross the fracture line. Should never cross the fracture line, because it will hinder in the union of the fracture. So only screw that can cross the fracture line is the lat screw, which is not part of a plate. So this lat screw should not be used as a plate screw. This should be used in other direction if it's a very long oblique fracture. Only a plate screw can go through the plate, but plate screw should never cross the fracture line. Now coming to the basic bone plating procedure, plates are nothing but devices that are applied to the bone for the purpose of providing rigid internal fixation. Rigid is the term that should keep in mind. Rigid means when there are all the fracture forces that we have seen in the first slide, the different forces that act on the fracture. Post-operatively, when the animal ambulates on the operated limb, the implant should withstand these forces, so we call it as a internal fixation. And screws, there are screws that fasten the plates to the bone, they maintain the bone fragments, and hold the fragments. Now coming to the plates, their classification, their development and all. The traditional round hole plates, there are classified as three basic categories of plates. Initially, when the orthopedics started, when the orthopedicians started using plates as a method of fixation, there used to be plates with the traditional round hole plates, with their like Sherman, Lane, Venable, and Burn plates, and they are usually applied without any compression. In that stage, there was no idea of compression to be created at the fracture site. So only a round hole plate. So in round hole plate, the screw can be applied to the bone through the plate in only one direction. We will see these plates in a subsequent slide. So it is only in one direction the screw can be applied. So after that came the concept of the AVO has developed the concept of compression, and we have plates like dynamic compression, low contact compression, and locking compression plates. We will see them. And there are certain, apart from long bone fractures, we have certain particular area fractures where we need certain plates, specialized plates like reconstruction plates, triple pelvic osteotomy, T plates, establer plates, cuttable plates, venable plates, veterinary cuttable plates. So these are other plates that have evolved based upon the specialized area of the fracture. But for all long bones, we either use a round hole plate or plates that are with oval. So coming to the plates that are with round hole, we have the Sherman, semitubular, and venable plates. Now, if you see the figure of a Sherman bone plate, the hole is found here, and when you apply a screw, you can apply a screw in only one unique direction. So you cannot give an angle to the screw when you are applying to the plate. Similarly, the same. So the advantage of Sherman plate is between two holes there is a notch. So there is a notch between the two plates. So only little area of the bone will be covered by the plate. So that is one advantage. The other type of plate is a semi-tubular plate with again a round hole where you can apply a screw in only one direction. And this because the area of the plate is more, this will be occupying more surface area of the bone than it is applied for fracture. And coming to the venable plates, these are the plates with very holes with the provided with the distant apart, again with the round holes, and because it is a there is no constriction between two holes like a Sherman plate, it is again going to occupy a larger area over the bone surface. Now now the concepts and now the challenges have started appearing before orthopedician. Now the challenge now is attainment of interfragmentary compression and primary bone healing without radiographically evident callus formation. So that was the primary challenge encountered by, because the school of thought in those days was a bone it should heal without any radiographically evident callus. So if you go to the basic idea of a callus formation, where bone heals by either by endoscopic callus or initially by periosteal callus, then again it remodels. Sometimes it will, depending upon the implant you are using, it can be both endoscopic and periosteal callus. But the thought in those days was that the callus should not be visible on a radiograph when a bone heals, and bone should heal by primary healing. The primary healing is direct Haversian system, direct recanalization, without any stages. If you go to the stages of fracture healing like fibrocartilage, mineralization of soft callus, formation of hard callus, remodeling of the hard callus. So these, because they thought that primary healing will take lesser time, and it makes the patient ambulate very early, and because the secondary healing takes time for the callus formation and mineralization of the callus. So the thought in those days was to attain a without radiographically evident callus, the union of a fracture. So that was the major challenge at the in front of orthopedicians, and so much of research was done both in human orthopedics and veterinary orthopedics to develop a plate which can cause compression when it is applied as a source, as a means of fracture treatment. So the result of that is the development of a plate called compression plates, And compression plates between the fracture segments reduces the fracture gap as it increases the interfragmentary stability. Now they are called dynamic compression plates because they are self-compressing. The dynamic, as the name indicates, dynamic is on its own. If you apply this plate to a fracture following all the principles of PCP, the plate itself can create a compression at the fracture site. So if you create a compression at the fracture site without gap at the fracture site, there won't be any motion at the fracture site. That micro motion which will be seen once the patient starts weight bearing is nullified because of reduction in the fracture gap. And because there is no micro motion, there won't be callus, radiographically appreciable callus, and bone should heal by primary healing. So that was the concept of development of dynamic compression plate. And it uses a principle called as rolling ball principle to allow axial compression using special load drill guide to position the screw hole eccentrically in the plate. So these are the dynamic compression plates of different thickness and different sizes. So this is a 2.7 dynamic compression plate. This is 3.5 dynamic compression plate. So this is the 2.7 plate when you see from the top. This is the lower or the ventral aspect of the plate. Again, this is the dorsal and ventral aspect of the plate. So the rolling ball principle or the basic, the engineering that is developed in the dynamic compression plate is this sliding hole that we will see in the different cross sections also. So this is the middle part of the plate. These screws are for one major fragment. These three holes are for other major fragment. And if you see carefully the structure of these oval holes, these three oval holes are directed in this direction, and these three holes are directed. So always at the middle of the plate, the holes are on either side are divided in such a manner. So this is a more clear picture. You can see this hole, this slide is directed in this direction, whereas this slide in opposite direction after the middle of the plate. So dynamic compression plate, this name is derived from a design of a screw holes causing compression. So the standardly available DCP, depending upon the size of the dog, weight of the dog, and the type of fracture, you can select whether you want to use a 2, 2.7, 3.5, 3.5 broad, 4.5, 4.5 mm broad. So the 2, 2.7, 3.5 neither will tell you about the width of the plate nor about the thickness of the plate. These numbers indicate that the size of the screws these plates will engage. Suppose I say 2 mm, that means this is a plate where a 2 mm screw will hold the bone with the plate. If I say 2.7, it means you require a 2.7 mm screw. Whether it is cortical or cancellous, that depends upon the area of the bone. I say 3.5, that means it takes 3.5 mm screws. So this is a 3 point, suppose for example, this is a 3.5 mm dynamic compression plate. You see the construct of the hole here. This is the mid part of the plate. This slope is in this direction, whereas in the opposite direction, the other 4 holes is in the opposite direction. So this place part of the plate should come over the fracture line when you are operating. Okay, so because I said it is a 3.5 mm DCP, it is neither 3.5 mm width nor 3.5 mm thickness. It is only that it takes 3.5 mm screw, whether it is cortical or cancellous, it depends on the area of the bone you are operating. Now, how to fix a major steps? You have to select the plate, whether, as I said, suppose you have selected the 3.5 system, it comes in 5 hole, 6 hole, 7 hole, 8 hole, 10 hole, 12 hole, depending upon the length of the bone, you can select the plate. Now, to drill a hole through the plate, you require a drill sleeve. Drill sleeve is nothing but a sleeve through which you pass the drill bit and you should do the drilling. Why we should use a sleeve means when you are drilling, you will be drilling with either a handheld drilling machine or a battery operated or an electrical drill machine. So because that works in a very high RPM, when you drill through the plate, there is a chance that the drill sleeve can slip over the bone. So to prevent that slipping of the drill bit over the bone in high RPM, we use this drill sleeve, where we place the drill sleeve in the hole of the plate and we start drilling, so that the drill bit will go in exactly the direction which you want to drill. So these are the drill bits. Suppose the drill bits again, they vary according to the size of the plate. Suppose I said 3.5 mm plate, it takes 3.5 mm screw. For a 3.5 mm screw, you should drill with a 2.5 mm drill bit, because the drill bit is always smaller than the size of the screw. So because first we have to drill, then we have to use a tap sleeve. Tap sleeve is the one which helps the hole that was drilled with a drill sleeve to tap. Tap is nothing but to make the threads on the bone for facilitating the screw to sit in those threads exactly. So that is what we call tapping. So this is the tap with a T handle, and the end of the tap will have these threads. Suppose I said 3.5 mm, 3.5 system of the plating. I will use a 3.5 mm screw. The size of the tap will always be same as the size of the screw. The size of the screw will be same as the system you are using. Suppose 3.5 mm system of dynamic compression plate, you use a 3.5 mm screw, for which we use a 3.5 mm tap. And the drill bit is always lesser diameter than the tap diameter or screw diameter. And you need a screw of sufficient length and a screwdriver which should fit exactly in the head of the screw to fix the screw through the plate. Now, what are the range of fractures that can be treated with a dynamic compression plate? So, we should classify it according to ASIF or to other system of grading like grade 1, 2, 3, 4. So, these are proximal third oblique fractures, or femur, or mid-shaft comminuted overriding, or distal third transverse radius ulna, or distal radius ulna oblique fractures, and mid-shaft radius ulna, distal third radius ulna, proximal comminuted tibial fractures. So, are these fractures with the fissures in the one of the fragments? So, these are the different range of fractures that can be and that are indicated for the fracture through the plate. Now, where a plate should be placed. Now you have selected a plate, you have selected the screw, you have selected the bit, you have selected the tap. Now, which part of the bone is the plate should be applied? This is one of the most important biomechanical aspects that a surgeon should keep in mind. Because every bone, every long bone will have two surfaces. One is a tension surface, the other is a compression surface. Okay. Now, the plate should always be placed on the tension surface of the plate and not on the compression surface of the plate. So, see, this is the bone, and this arrow indicates that the load here is nothing but the weight bearing process once the animal starts walking after the surgery. So, now this is our fracture line. This is the plate applied on the tension surface of the plate, not on the compression. These are the screws, 3 screws in the distal fragment, 3 screws in the proximal fragment. One screw crosses 2 cortices, the near cortex. You are working from here, so you are putting this plate on this side. So this is the near cortex, this is the far cortex. So for each fragment, you will be crossing 3 into 2, 6 cortices. So here also 3 into 2, 6 cortices. So the basic principle of any ASIF principle of application of a plate is you should either use at least a minimum of 3 screws or 6 cortices on each major fragment. Now, this is the wrong placement of the plate on the compressive side of the bone, whereby it again resulted. So, compressive surface, if you already there is a compressive area of the bone, and a plate will undergo compression, and there will be a fatigue failure of the plate. We call it as bending abnormality. The plate will bend if you apply it on compressive phase, and again there will be grating at the tension surface of the bone. So always try to put it on the tension surface of the bone. Now, what are these tension side of the bones? Different bones have different surface. For example, you are working on femur, the tension side is granulateral. Tibia, it is granulateral. Humerus, majority of the long bones, it is mostly granulateral. Even for radius, it is cranial, not granulateral. It is totally cranial. Ulna, we usually do not fix a plate for ulna unless it is a very heavy breed of dog. Ulna, it is the caudal aspect, and for the mandibles, it is the dorsal aspect of the mandible. But if these principles, sometimes they are not placed on the tension side due to impracticability or some added difficulty. One best example where this is not possible is tibia. Why? Because tibia, the approach to the tibia is on the medial aspect because there is very least musculature on the medial side. On the lateral aspect, you find a lot of musculature. So the application of tibia usually we do on the medial side, bypassing or surpassing the AVO principle of applying a plate on the craniolateral, which is the tension surface for the tibia. Now, application of plates. Plates can be applied both in different forms. The same plate, like a compression plate, like a neutralization plate, or a bridging or a buttress plate. And it depends how a plate is applied. There is no plate like a neutralization plate. There is no plate like a buttress plate. Same compression, dynamic compression plate can be used as a neutralization, can be used as a buttress. Only thing is the modality of using this plate will vary. The plate will remain the same. For example, a 3.5 mm DCP can be used both as a compression, neutralization, or a buttress plate. And when we should use this compression plate? When it is when the fracture is transverse or a very short oblique. Where the angle is less than 45 degrees, there this compression plate is indicated and is feasible also. Whereas neutralization is a plate where there is a comminution. Comminution is when there are more than two fracture lines joining each other. We call it as a comminution, and the angle is more than 45 degrees. Bridging plate, also called as buttress plate, is used when a segment of the bone is severely comminuted, and we sand this area of comminution of the bone without applying any screws, and this acts as a bridge. It will bridging means it will bridge the gap where there is severe loss of bone, and it will only hold the bone in the healthy aspects of proximal and distal area of the fracture. So this we call it as a bridging plate. Now, what actually are compression plates? So they generate, this is important because the name given to the plate is a dynamic compression plate because it is generating axial compression of the fracture. And how it generates, we will see. And pre-stressing of plate by bending it at the fracture surface. So pre-stressing is nothing but giving the shape to the plate according to the shape of the bone. Pre-stressing, that means pre of what? Pre of application. What you are doing, you are stressing. Why you are stressing? Because our plates are straight, but the bones are not straight. What you are using are straight plates, but our bones are always curved. You take a humerus, you will have a huge musculospiral groove. You take a distal femur, you have a cranial bend at the just above the condyles. You take the tibia, it is very broad in the proximal aspect, very narrow in the distal aspect. So likewise, our bones are not straight, but the plates are straight. So you have to shapen the bone plate before you apply it to the bone according to the contour of the plate. The term used for this process we call it as re-stressing. Before application, you are stressing the plate. And usually we will have a 1 to 2 mm gap at the fracture site and insert at least 2 screws nearest to the fracture with a loaded position that we will see in detail. So now the same plate, different situations. The situation here is a mid-shaft transverse fracture. Now this is the head of the femur, so this becomes the medial aspect of the femur. This is the lateral aspect of the femur, and the tension surface of the femur, which we have studied earlier in this slide, is the cranio-lateral surface. So this is the surface where the plate has to be applied. So this is the tension surface. Now this is a plate applied in the form of a dynamic compression. So you can see that means even though it is schematic diagram, there is no gap at the fracture site. Okay, and these fractures heal by direct diversion system generation, and they heal by very minimal either endosteal or periosteal caries. And radiographically, you may not be able to appreciate the caries at all, even after healing. So that was the concept in those days, and these plates are developed for that very concept. So these are dynamic compression plates. Now neutralization is, now you can see this is one fracture line, this is another fracture line. So there is a very big wedge here. So we cannot use a compression here because the chances when you use a compression in such situation, the fracture may collapse. So the same dynamic compression plate. Again, this is the tension surface of the bone. This is the head of the femur, so medial surface. Plate placed on the tension surface, but the plate is used the same dynamic compression as a neutralization, where it takes weight bearing load, but there is no compression of the fracture. Now these fractures may heal with some amount of callus after the normal time of healing. Now buttressing is where there is a very huge loss of bone at the fracture site. We cannot use any of these screws. As I said in the initial stage, that the screw which passes through the plate should never cross the fracture line. So any of these fracture lines, your screw should not cross unless it is a lag screw which goes beyond and away from the plate. So we are not using any lag screw, only a plate screw is used. So none of the plate screws have crossed the fracture line, and this bridges the loss, a severe loss at the fracture site, and it will hold the bone only at the proximal and distal healthy part of the bone. So 3 screws are used in the one of the proximal fragment and 4 in the distal. Now these are the few radiographs, the immediate postoperative radiographs which we have taken in different situations where the plate is same. The same dynamic compression plate is used in all these fractures. One is a femur, the other is radius, the other is femur, the other 2 are femur. This is a dynamic compression plate. Here we are not even able to appreciate the fracture line because it was a simple transverse fracture. The plate is applied on the tension surface, the lateral surface, and the fracture line is not appreciable. Whereas here also distal third, transverse, radius ulnar fracture. Now you can see the gap at the fracture site, but because a compression mode is used, you cannot appreciate the fracture line here. 3 screws in the distal and 6 screws in the proximal fragment. Now the same dynamic compression plate is used as a neutralization plate because there was an oblique fracture. You see the fracture line here very clearly. There was an oblique fracture and the compression is not recommended here. So it is used as a neutralization. And in this last situation where there is a gap and loss of fracture, bone at the fracture site, here we are using it as a bridging or buttress plating, and where there is neither you can use a compression or neutralization, only it will bridge the gap and it will hold the fragments until there is a union. So the same plate and different situations has different types of plate. Now the most unique feature of this dynamic compression plate which we are discussing is a precisely engineered internal glide pathway. So it is nothing but the sloping of the screw that was, I have also showed you, I zoomed in and I showed you the slope of the screw hole in the plate. It is an internal glide pathway found in each hole of the plate. I have shown you how the direction of the slope varied on either halves of the plate. One half it is in one direction, the other half it is in another direction, and it allows the generation of interfragmentary compression when you insert a load screw. So this is the basic of a dynamic compression plate, the engineered glide pathway, and this we call it as a sliding ball principle or spherical gliding principle, where the screw head is a ball. We will see all the schematic diagram. Here the screw head will act as a ball, and the oblong plate hole is an inclined plane, where the ball slides over that inclined plane when we apply the screw through the plate. Okay. Now the screw head will slide towards the center of the hole as screw is tightened. There will be a horizontal movement of the bone beneath the plate, and it is done on either side of the fracture line so that there will be a compression, and you use drill guides. Drill guides for compression, drill guide we have discussed, that is a drill sleeve or drill guide, which will help you to drill the hole on the bone. We have a loading and a neutral position that we see. So the cut surface of a dynamic compression plate, when you cut the plate into half over the screw hole, this is how a DCP will look like. Now we are trying to answer how compression will occur. So this is a hole in a DCP, and see this sloping here. This is a normal hole here, and this is a sloping hole slope of the hole that is created. When you use a load guide, so when you use a load guide, you will be drilling somewhere not exactly in the center of the hole, but abaxially or eccentrically, so that when you tighten the screw, the head of the screw will slide into the center. And when you use a normal neutral guide, you will be drilling exactly in the center where there won't be motion of the screw. If there is no motion of the screw, there won't be motion in the fragment either. Now have a closer look at these two different colored drill sleeves or drill guides which we use for plating purpose. So the yellow color coding is for a loaded drill guide. The green color coding is for neutral drill guide. What is a load drill guide and what is a neutral drill guide? See the undersurface of the, so this hole you can see, you are able to see this is the sleeve here, and we pass the drill bit through the sleeve and we drill a hole. So this is the hole in the sleeve. See the difference in the holes of the drill sleeves. You have seen the structure of a hole in the plate. That is one engineering marvel in the plate design, and this is another engineering marvel in the sleeve of a drill sleeve. One is the hole of a loaded, so LO is always loaded, is eccentric, it is not in the center, and the hole of a neutral guide is always in the center. Okay, so these two loaded and green, neutral, are available in one single sleeve, and it is the surgeon's choice. If you want to give a compression, he should use a loaded guide. If you want to use the plate as a non-compression plate, like a neutralization plate or a bridge plate or a butter plate, he should use a green sleeve. So both these ends are present on a single sleeve, which I have shown earlier. Now what exactly is happening? See, this hole here is indicating the hole of a neutral guide, which is exactly in the center. This hole here is indicating the hole of a loaded guide, which is not centered, it is eccentrically placed. Now if you use this drill sleeve and you use a drill bit and you put a hole in the bone, you will be putting exactly, so you can see the slope here of a dynamic compression plate hole. So you are not using this slope, but because you are using a neutral guide with a central hole, the hole will be made exactly in the center. Now you drill a hole, you tap the hole, you measure the depth of the hole, and you apply a screw. It will go in one straight direction without any motion of the fragment. Now this is what when you use a neutral guide. When you use a loaded guide, when there is an eccentrically placed hole, now where you are drilling when you are using this sleeve, you are drilling not in the center of the hole, but eccentrically over this slope. Now this slope is masked by the screw. Now you have drilled a hole, you tap the hole, you measure the length of the hole, you select a screw, and you are started applying the screw with the help of the screwdriver. Now what is happening? See carefully. So until this screw crosses, this is the bone, this is the near cortex, this is the medullary canal, this is the far cortex. Until the screw crosses the near cortex, medullary canal, and when it starts engaging the far cortex, then the actual sliding phenomenon will occur, because the head of the screw will start sliding sliding through the angle of the whole of the plate, and the head moves in this direction. When the head moves in this direction, it will take the fragment in opposite direction. So this is the fragment of the bone. So the fragment of the bone moves in this direction, and the screw head. This is a micro motion of which is not appreciable by a naked eye. It is only a very micro motion. 1 mm maximum is the movement you get, and it provides 1 mm compression, and screws are placed eccentrically, whereas in neutral, the hole is drilled in exactly in the center where there is no displacement of the fragment. Now it is your choice whether to use a loaded guide or a neutral guide, and the basic difference is the hole of the sleeve. Now see the screw placed in neutral mode in a dynamic compression plate. So this is the slope of the hole in the plate. Because it is a neutral, the hole is in the central. You drill the plate, the screw will go straight in one direction without movement of the fragment. Now what happens this is a screw placed in compression mode. We are using a loaded guide. See the eccentrically placed hole in the sleeve. So you are not drilling in the center of the hole, you are drilling somewhere here. So when you drill and tap and start applying the screw, when the screw starts engaging the far cortex, it will start sliding. See the sliding here? It will slide over the screw and the fragment will move. So in this direction, this is our fracture line. This is the gap which we want to reduce. This is the gap which we want to reduce, and this is the gap where a compression is to be created by using an eccentrically placed screw. So a very simple anomaly or a design where this is sliding ball. Sliding ball is nothing but the head of the screw, and this oblong slope is nothing but the slope of the hole in the DCP. Now this ball slides. When it slides, it takes the fragment in opposite direction. So again, similarly here. So okay. Now this is how the screw head will slide when it start engaging. So this is the plate, near cortex, medullary canal, far cortex. Now so this is our fracture line. So this is the fracture line. So when you apply the first screw, the fragment on either side of the fracture line, this is the fracture line, one on the right side, one on the left side, should be done in a loaded manner. That means you should use a loaded sleeve, and either on either side of the fracture line, you should use the load guide. For the rest of the screws, these are the rest of the screws, you can use a neutral guide, because whatever motion, interfragmentary motion that will happen when these two screws are placed. So beyond that, there won't be much motion. So these screws can be placed using a neutral guide. Only screws on either side of fracture, you can use a loaded guide. Okay. Now this first screw is placed. The movement of the fragment will be in this direction. When first screw is placed in this fragment, the movement of the fragment will be in this direction. So the second screw, and when you tighten the screw, now see what is happening to the fracture gap here. It is initially when the first screw, now the second, now the third. See the fracture gap from here to here. There is absolutely no gap. Now you have created a compression at the fracture site. This we call it as axial compression, and this we have created without any external device being applied to the bone. That is the reason why we call them as a dynamic compression plate, by virtue of the design of this hole in the plate and by virtue of the drill sleeve difference, we are creating this compression. Now, what type of fracture healing you expect here is primary fracture healing without any soft callus, mineralization, or a hard callus formation. It is a very minimal radiographically appreciable callus, and this will happen very quickly, and that is the reason why this method of compression is preferred some 30-40 years back, and it was considered as the golden era of bone plating when dynamic compression plates were introduced. Now this we have discussed the idea of pre-stressing. Pre-stressing is nothing but, see, I said our plates are straight, but the bone will always have a curvature. So we use these structures called as templates. These are aluminum made, easily malleable. They can be autoclaved, and based upon the pre-operative radiographs, you have to select these templates, and these templates should be put in pack for autoclaving. They are autoclavable templates, and before you select the plate, and when you open the fracture site, you use this template and press this template over the bone, and exactly according to the contour of the bone. Now you remove the template. Now you got this template with a curvature. Now looking this curvature, you have to pre-stress the plate using these plate benders or pliers, or this is what we call as plate press. This is called plate press. What we do is we engage the plate here, and with the help of these benders, we give shape to the plate. Now this shape to the plate, given to the plate, should correspond to the shape that is given to the template, and this shape of the template should correspond to the contour of the bone. Then when you apply this plate to the bone, it will exactly be according to the contour of the bone. So that is the pre-stressing what we do before application of the plate. Now this is a plate used in a very severely comminuted fracture by a bridging plate without any screws at the fracture site. Now you see the stages of healing. Here we have used a dynamic compression plate for a mid-shaft transverse fracture. Now, as I said, we have used the compression. There is no appreciable fracture line evident in the radius. And now this is after a few days of follow-up. Now this is a final healing. Even though ulna is showing, we have not fixed ulna. Ulna is showing certain amount of callus, exuberant callus. The radius, there is a minimal callus, and even after remodeling, we are not able to appreciate the callus formation because it is healing by primary intention. This is a clinical outcome. Actually, this is a video. Unfortunately, so this is just on third day of the plating. The animal is walking normally on the limb. And what are the advantages of doing this plating is what we get is anatomical fracture reconstruction and healing with little or no external callus. This was considered as advantage. Let me reinstate that this was considered as advantage. Little callus was considered as an achievement in fracture healing, an achievement in decreasing the time of fracture healing. So that was the reason the development of DCP. And most forces acting at fracture are resisted, and but some people say that plates are very poor against the bending forces. That we'll discuss. And rigid fixation, and so very early brain-free mobility. Now there is one disadvantage when we use this highly rigid implant with compression at the fracture site. What we call it as mechanical stress protection. Stress protection is what is stress? Stress is nothing but when the animal walks and the bone is subject to normal mechanical stresses of the body weight and the opposite ground reaction, and the stress is very much required for the cell turnout of the bone. The stress is very much needed when the bone has to grow in length or when the bone has to be maintained. The stress across the bone is very much needed. So the stress is the biggest impulse for the bone to be maintained. But when you do a plating, the area under the plate, area of the bone under the plate is protected because the plate will take the maximum load because it is having higher elasticity. So the plate is a higher rigid material, so it will take the majority of the load. So that part of the bone under the plate is protected from the stress. Now, why if it is protected from the stress, that will have a very reduced blood supply, and that part of the bone undergoes severe osteoporosis. And when you remove the plate, there are chances and there are incidences of a refracture after removal of the plate. So that is the biggest hindrance of. So this is how the primary healing was started getting a negative comment that primary healing is not advisable. But this primary healing ruled the world from some few decades of orthopedics, both in human and veterinary. Now, the next challenge in front of orthopedician is the effect of compressing the plate to the bone is so deleterious that the vascularity and viability became contentious issues. So, which we have discussed, that area under the plate is always, the vascularity is always impeded, and it reduces the amount of the impetus was to reduce the amount of plate that is in contact with the bone. We want to reduce that contact area, and this led to the development of what you call limited contact dynamic compression plate. So what is this limited contact is? It decreases the frictional forces between the plate and the bone. Thereby, there is some chance of development of vascularity under the plate, so that the problem of osteoporosis is not seen. But when this low contact dynamic compression plate was developed, they assumed that it will decrease 50% of vascularity problems than compared to a dynamic compression plate. And these are the low contact dynamic compression plates. The upper design of the plate is very much similar to a dynamic compression plate. The only difference is on the undersurface of the plate, you have these notches. So you can see these are the notches in between the holes of the plate, where there is a probability of development of certain blood vessels once the plate is applied. for the part of the bone under the plate. But after Doppler research, after certain biomechanical research and certain cadaveric studies, it was found that the osteoporosis induced by a dynamic compression plate and osteoporosis induced by a low contact dynamic compression plate, there is no statistically significant difference, and both will have caused similar osteoporosis, whether you use a dynamic compression plate or a low contact dynamic compression plate. So this is a low contact or limited contact dynamic compression plate. See the undersurface of the plate. The photo here is provided to show these notches. So the plate or the above surface is same as a DCP, but these notches will allow certain vascularity under the plate to develop once the plating has been done. Again, they are available as 2.7, 3.5 and 4.5 mm sizes. The next challenge for an orthopedician is the in vitro mechanical studies have reported that bending and twisting of plates resulted in significant loss of plate thickness when plates are contoured according to the bone contour. So this we have studied earlier, the pre-stressing concept, where we pre-stress the plate according to the contour of the bone. But as I said, the advancements in biomechanical studies have taken up. They have studied the forces in different situations like bending, shear, and all. So they have concluded that when you pre-stress a plate, the plate will lose majority of its thickness, and the pre-stressing should be avoided. That means the plate, even though it is a straight plate, need not be contoured according to the contour of the bone. So this challenge later was resulted in development of the most advanced plates, even for in day-to-day, in up-to-date orthopedic field, locking compression plates. So development of locking compression plate is a compression plate. The locking compression plate is where the screw which you are using gets locked with the plate, whereby the pressure of the screw will not be on the bone, but will be on the plate, because it gets locked with the plate, and plate should not neededly have a complete frictional attachment with the bone, thereby decreasing the problem of vascularity and problem of osteoporosis, and there is no need even to contour the plate according to the contour of the bone, thereby preventing the rigid stiffness of the plate. So so many advantages of locking compression plate, and they have threaded holes that accept lock and with locking head screw. And the biggest development in a locking compression plate is to have a combi hole. A combi hole is the one where half of the hole will have a thread, the other half will have a similar hole like what we have seen in dynamic compression plate. So the same plate can be used in wide variety of model. For example, so let me show you the plate in detail. So this is a threaded part of the hole. This is a sliding hole that we see in a dynamic compression plate. So this is a locking compression plate. This is a normal cortical screw when you use in this part of the locking compression plate, and this is a locking head screw when you use in the threaded part of the hole. Okay. Now this blue screw is a threaded screw. You can see the threads that gets locked in the threaded part of the hole, and the other screw is a normal screw which gets it is not locked, but it is placed in a sloping hole, that is as a dynamic compression hole, whereas the threaded part will be vacant. So this is the threaded part of the combi hole, and the sloping or a sliding ball slanting hole of a combi hole. Now this will take a normal cortical screw, and the threaded part will take a threaded locking head screw. So these are locking head screws which we have already seen with the threads in the head of the screw. So the screw will get locked with the plate only when the head reaches the plate. When the head reaches the plate, it must have crossed both the cortices. Now this is a locking compression. So this is a 3.5 locking head screw, and this, see the construct of the holes here. This is the 8-hole plate, 10-hole plate. 10-hole plate. This is the exactly middle part of the plate, and see the construct of this. So this is the on this side the locking part is here, the sliding part is here. The other surface, other side of the plate, other half of the plate, the locking part is here, the sliding part is here. So if you want to use a compression, you can use this part of the hole, combi hole, and it creates a compression in this direction. If you want to use a compression on the opposite side, this part of the hole is filled, and this will move the fragment in this direction, and because the fractured line will be somewhere here, and this is a combi hole. And one important aspect which should be kept in mind, because it's a combi hole, the area for drilling will be more. And suppose if you want to use a threaded part of the, you want to use it as a locking plate, then you have to drill only in this part of the combi hole. Where if you suppose if you apply a hole here, this will not engage the threaded part of the plate. So for that we use this locking drill sleeve. This is a normal drill sleeve. With this you cannot create a compression, but only thing is the threads which you are seeing here will come and get locked with the plate here, and through this sleeve you can drill a hole so that it will exactly drill at the locking area of a combi hole. So that is one important locking drill sleeve. So a fixation of a locking compression plate. So this is a locking drill sleeve which gets locked with the threaded part of a combi hole. Bit which we use through the drill sleeve, then we select a screw. This is how a locking. So now these screws are locked with the plate. If you do it on a bone, they will lock the bone and a plate, and this is how they lock the compression. So these screws, this is a half of the plate. These screws are in this direction, and the other half that screws are in other direction. So this is a distal third radius ulnar fracture that was fixed with a 6-hole 3.5 locking cortical screw. You can see a combi hole where we have not used any compression here, but we have used a threaded part of the hole where all the screws are placed in a thread. See here, we have not used this. So this is the mid part of the plate. These are the threaded parts where the screws are up. Now the basic difference when you use a conventional dynamic compression plate, when you use a locking compression plate is, see, this is the plate, this is the hole of a plate through which we apply a screw. This is the fore cortex, medullary canal, distal cortex. When a normal conventional plate is applied, the plate is in close contact with the near cortex, causing a lot of friction and less chance of vascularity of this part of the bone. Whereas when you use a locking compression plate, this is the plate, this is the hole for a screw, and this is the screw, this is near cortex, medullary canal, fore cortex. You can clearly see that there is a sufficient gap between the plate and the near cortex for the vascularity to remain normal. So this is how, that is the reason why these locking compression plates are called as point contact or internal fixators. They act as internal fixators without the need to contour the plate, without the need to have a snugly friction between the plate and the. So this is the same animal where the locking plate has been applied for distal third radius ulnar fracture, and this is complete healing. So you can see here there is a gap between the plate and the bone. In spite of that, because it doesn't require the complete contouring of the plate and close application of the plate over the bone. So this is the video. Again, a video not working, but animal is putting weight on it. Now, the further next challenge encountered by an orthopedician is smaller fracture fragments. And suppose the one of the fragments is normal, the other fragment is very small. That are fractures very close to the joints, where standard 3-screw placement per major fragment is impossible. So if you encounter such fractures, now this is a challenge. So here you cannot have, be in a position to have 6 cortices locking. We have discussed that earlier, that 3 screws or 6 cortices per major fragment, which is not possible. So how to counteract or how to face these fractures? So this is an example where it is not possible to have a 3 screws in these because of smaller fragment. Again, a smaller fragment here. So the answer for this is locking compression plate. So locking compression T plates will have a T shaped at one end and a normal locking compression plate on the other, and the plate is described based upon the number of holes in the shaft. So this is a normal 3-hole for every size of the plate. See, this is a 3-hole plate, 4-hole, 5-hole, 6-hole, but this T will go to the distal fragment or the smaller fragment. See, the idea here is when there is not, it is, for example, such a fracture when it is not possible to have a 3 screws. So this T will help you to have 1, 2, 3, and at least 1 screw in the distal, and the rest of the fragment, rest of the screws in the proximal fragment. So the principle of 6 cortices can be satisfied by using these T plates. Same, you can use a normal cortical or a locking plate with these locking T plates. So example of few case studies where locking T plates are used are distal femur, almost epiphyseal fracture here, where a locking T plate with 3 screws. See here 6 cortices principle is satisfied. You can see 3 screws because of the availability of T and 4 screws in the proximal fragment. Similarly, very small fragment in the closer to the joint, called fragment of the radius ulna. You can see 4 screws here in the distal and the rest of the screws in the proximal. So this is after 60 days, the complete union of the fracture of the distal femur and the animal putting weight immediately on the limb. Next challenge encountered by the clinicians was to, if it is not possible to lock both the cortices, then a compact Unilock system has been developed. They come in different sizes like 1.5, 2, 2.5, 3, and 3.5, and they come in very lengthy plates. What you can do is you can cut these plates according to the requirement of the length of the bone. And the advantage of these plates is here also it is not a combi hole, but it is only a locking hole, and with a locking head screw we can lock the screw with the plate. And the advantage here is you can use a unicortical screws. So there are situations where bicortical screws may not be placed. So with these plates, unicortical screws can be placed, and it gives an equally rigid fixation. So the distal oblique humerus fracture treated with a compact Unilock system with one. See, this is crossing the fracture line, so this should not go through the plate. This is a lag screw, and the rest of this plate holes are through the plate. See here, you can see this is a Unilock, and one or two as a bicortical screws. Now, if you see carefully, because it's a locking plate, see the area between the plate and the bone. There is a significant area which we cannot appreciate in a dynamic compression plate. So this is a frictionless area, and there is a scope for vascularity after plate application, and there are less chances of development of osteoporosis in this part of the bone under the plate. Again, an oblique distal third radial fracture treated with a compact. See here, 1, 2, and 3. All 3 are Unilock screws. Only one in the other of the extremities are bicortical screws. So the advantages of such system is the contact between the implant and the bone is kept stable using screws which function as a locked threaded bolts and prevent the plate pressing on the bone. So we have seen that there is a significant gap between the implant and the bone, and less subsequent osteoporosis under the plate. So interlock screws offer superior stability with fewer screws. So that is the advantage. So it doesn't require a very massive exposure of the bone, massive disturbance of superiosteum, massive soft tissue disturbance. Even a smaller screws can help in stabilizing the fracture, unlike a dynamic compression. Now the next challenge in before an orthopedician is, what if there are displaced fracture in young animal 4 months, 5 months, 6 months before the attainment of skeletal maturity, where the cortices are very thin, medullary canals are very big, the holding capacity of the cortex is very, very poor. The major problem in such cases, if you want to use a plate, is the pull-out. See here, you can see the screw got pulled out. The pull-out strength of the screw is more, and the thin cortices are the challenge. So to overcome this challenge, the next procedure. So this is one case, very young animal, you can see an open epiphyseal plate, very thin cortices, broader medullary canals, and fractures, displaced fractures, they cannot be amenable for external coaptation, so they have to be fixed by internal methods. So we have developed again a new entry is elastic plate osteosynthesis. Elastic plate osteosynthesis is nothing but using a longer plates and with minimal locking in one of the major fragments like one screw or two screws, and we will be bypassing the fracture area without disturbing the fracture hematoma, and only very few screws are used to lock the proximal and distal fragment, and we use a lengthier plate. Either you can use a veterinary cuttable plate or venable plate, very thin plate, because only in a very young animal we use such elastic plate osteosynthesis. And implant elasticity allows rapid formation of a very huge periosteal callus because of motion. Because motion is expected because we are not doing a rigid fixation here. And the longer the plate and farther the screws away from the fracture, longer the plate, farther the screws from the fracture site, there is a greater elasticity and lower pull-out forces exerted on the screws. Now the next challenge is, what if it is a distal communicated intra-articular radial fracture? So very commonly, and these are very specific for veterinary orthopedics, intra-articular radial fractures in combination with dislocation of the carpal bone, in combination with fractures of the metacarpal bones or carpal ligation. So what will you do in such situations? Because normal plates may not going to help in such situation. So we have a single or double-stepped hybrid carpal pan-orthodesis plating. Single or double-stepped hybrid carpal pan-orthodesis plating. So what exactly is single or double-step is, these are the plates with a single-step design, and these are the plates with a double-step design. So both are hybrid carpal. Why it is called hybrid carpal is, so this is a part of the plate, of a hybrid plate, which is used to engage the radius part of the bone. This part will be engaging the proximal row of the carpal, and this part will be engaging the metacarpal. So the system here is a step-down system. We call it as a step-down plate. Here this will be a 3.5 system, and this will be a 2.7. So you can clearly see the difference in the thickness also, and this tape is provided to accommodate the carpal joint, and sometimes you can have a double step to accommodate the second row of the carpal, and again this is 3.5 in the upper, 2.7 in the lower system. So a very bad fracture, an articular fracture of the distal labia ulna, not amenable for normal plating procedures. And suppose if it is also having metacarpal fracture and dislocations of the carpals, this SHCP or stepped hybrid carpal pan-orthodesis plating is a very good solution. So this plate is used with the 3.5. This the step 1 is a single screw for the proximal carpal. The rest of the screws for the metacarpal. This resulted in a very good healing, and this is after the plate removal. So it allows better anatomical fusion of the carpal and metacarpal bones. Now there is another system of plating, a more advanced system of plating, still in the process of trials. In few instances of human orthopedics, they are put into use and they are adapted into veterinary orthopedics. It is called a Switzerland-based company has developed this synthesis Pengo system or XPS plates. And the basic idea of this plating system is it will have a trial bar. Okay, this is the trial bar, and you have these shorter modules of the plate with the round holes. Okay, no compression or no locking system, and these modules are slide over this trial bar. This trial bar will be kept on the bone, and one of the module will be locked with the trial bar. The other will be in. So suppose this is locked module, and this will be in motion. So based upon this here it is where you get the fracture site. Based upon the type of fracture, whether it is a comminuted, bone loss, you can adjust. This will be fixed. You can fix it to the bone. Suppose this is a distal fragment. The proximal fragment, you can slide this module over this trial bar, and you can adjust the location of this module according to the site of the fracture. So the underside of the SPS plate will look like this. And the advantage of this here is you have two different modules that to be fixed over the fracture, one for the distal fragment, other for the proximal, or vice versa. So this is a bone fracture where the SPS plating system has been used, and here the modules are kept away from the fracture site and away from each other. This is the trial bar which you can see, and the fracture has healed with some exuberant excessive callus. This is after removal of the implant. Now, the same SPS system which was used when the modules are kept very close to each other at the fracture site without any gap between the modules. So this has healed with minimal callus because there is no motion at the fracture site. So this is the advantage of SPS system, that one module will be fixed to the trial bar, the other module you can adjust according to the type of the fracture. So lesser interface contact with the bone, because the module will never touch the bone. Only thing that touches the bone is the trial bar over which the module will slide. So very limited contact between the implant and the bone, and better outcome of the fracture. So the next advancement is called the string of pearls or SOP plates, where pearl means the screw hole will look like a pearl, and these screw holes are connected with each other by these internodes. So these internodes, they also come in different lengths. You can cut according to the size you require, and you can cut at the internode area. They are available as 2.7 and 3.5. Again, the 2.7 indicates that it takes a 2.7 screw, and 3.5 indicates it takes a 3.5 mm screw. Again, in SOP plate, you also have a hole with a threaded hole where you can use a threaded head of the screw. This is how a hole is drilled over the bone, and the screw is applied after tapping the bone. The advantage here is to contour without disturbing the stiffness of the plate or fatigue stiffness of the plate. The plate can be contoured according to the contour of the bone. This is the advantage we have. We have studied in DCP that it will significantly decreases the stiffness, but this is not so in case of SOP plates, and you can clearly see very significant gap between the plate and the bone without the chances of osteoporosis, and the plate is fixed over the bone. So this is a elbow fracture with an SOP plate, where the plate is contoured according to the contour of the bone, and this resulted in a very good fracture. And this we have used SOP for a diaphageal fracture, also for a distal radius ulnar fracture. This you can see the SOP plates with screws, and we have left the screw open without locking because there was a fracture here, fracture site, and see the reduction here. Now this is the outcome of SOP plating in a dog. You can see a dog walking on the operated limb very normally with complete weight bearing. Now the next challenge is how to preserve the local fracture. Now there is a shift from the stability to the local environment. So stability, we have seen so many different types of plates that have been developed to create a better stability without damaging the vascularity of the bone. Now the concept has reached to a point where the environment of the fracture site is also more important than stability. So now the concept is not to disturb the fracture hematoma. That is how the concept of biological osteosynthesis has developed, where that we will not handle the fracture site, but we will bypass the fracture site. The implant will be slided over the fracture site, and we will be fixed away, very far away from the fracture site, without disturbing the fracture hematoma, thereby attaining a process of biological osteosynthesis. So this is a schematic diagram for a tibial fracture, where you make a window away from the fracture site, you make a tunnel with a forceps, and this tunnel is used to slide a plate. You can use a lengthening plate, or you can use a veterinary cuttable plate, or you can use a locking compression plate for micro procedures. They call minimal invasive percutaneous osteosynthesis or plate osteosynthesis. For the radius ulna, we make these tunnels, and we bypass the fracture, and only at the ends of the long bone we fix the screws with the plate, thereby without disturbing. So this is how, without disturbing the for the femur, the tunnel is made and the fracture is blocked. So this is the immediate post-op where MIPO is used with 2 screws in the distal and 2 screws in the proximal fragment. So minimal hindrance to the fracture site, so that the fracture. Now, as I said, the importance was majority of the time importance was given to the stability, strength of the plate, construct of the plate, design of the plate, the biomechanics of the plate. But at times we surpass or bypass the basic source of initiation of callus and the concept of autogenous bone grafting. So, which is again, it is not only the stability, it is the inherent capacity of the bone to allow the callus formation, which should also be kept in mind. And you get certain situations in your daily clinical practice where it is not only the stability, but the initiation of callus should also be taken in care of. For example, so these are the radiographs of a distal radius ulnar fracture, and probably earlier treated with a fractional coaptation, probably a very simple fracture, no overriding, but this has resulted in a non-union, a typical non-union, where the medullary canals are closed, there is no initiation of callus at the fracture site, and there is no even signs of callus formation, closed medullary canals, and a very clear-cut fracture gap. So this, the non-unions, will never heal in the lifetime of the animal unless and until you create an environment by providing some initiation at the fracture site and some stable fixation. So I will provide you a case study. This is one animal that was presented with the history of 120 days of UP cast application. Even after 120 days, the X-rays have clearly shown the fracture gap, and the animal is total non-weight bearing on the affected limb, with the limb completely lifted up. So the answer or solution for such a non-union is autogenous cancellous bone graft. Is even today, in spite of availability of many grafting procedures like synthetic grafts, complex grafts, so many available procedures, autogenous, even in human orthopedics, autogenous cancellous bone graft is considered as a golden harvest from that can be collected intraoperatively from the same animal. The only disadvantage is the quantity. You have to select the sites where you get a better quantity of autogenous, and immediately you can transfer to the fracture site, and extra trauma will be created to the animal, but it is in the interest of the patient. Now see, this is for the same animal, we have used a dynamic compression plate in a neutralization manner because we have a fracture gap. We are not supposed to use a compression, and we have created, we have harvested autogenous cancellous graft from the data tubercle of the humerus, and the graft is placed at the fracture site after fixation with the graft plate. So this is immediate post-op radiograph, and this is the fracture site where the graft was placed, the same autogenous of cancellous graft. This is the animal on 15th post-operative day, where we started putting weight while standing at least. So the implant is intact, the graft is intact, and the animal started putting weight when it was standing. After 85 days, the animal started complete weight bearing, which was totally non-weight bearing, and you can see the radiograph after 85 days, the complete healing of the fracture site. So this, as I said, not only stability, you should also think in lines of initiation of callus in such cases. Now, certain complications of plating procedures, as I said, pull out of the screws is very common, and bending, particularly tibia, they are more prone. This we have discussed because tibia, the tension surface is the lateral surface, but we apply on the medial surface. They are prone for bending. So radius ulna, depending, are also prone for bending. Bending is the biggest complication. So this is how the plate gets bent, which requires implant removal and probably revision surgery. And the indications for plate removal: once the fracture has healed, implant becomes redundant. There is no way the implant can remain, and persistent sinus formation. In certain cases, which require removal, and in winter and months the animal feels pain, so it requires removal, or a liquid granuloma, sometimes animal keeps on leaking, and when plate becomes non-functional, these are all indications where the plate should be removed. So this we have started with the plate with a normal round hole plate where the screw can be applied in only one direction, and we have almost processed so many different types of implants with the different types of engineering marvels in these holes and in the sleeves, and the different types, shapes of plate contoured according to the need of the patient. And now we have come to a position where it is not only the stability, it is also the environment at the fracture site that will be taken care of. And now we are in the process, in the era of biological osteosynthesis, where open but do not touch or do not open, closed fixations. And because of the advent of certain imaging procedures like CM image intensifiers, and these are helping to do a closed fixation using these available implants. So the philosophies and techniques of treatment will change with time, but the philosophy that we exist to improve the care given to our speechless patients will last forever. So that is the basic philosophy we should rely on. And even though the philosophies of techniques change, our philosophy to give a better treatment should remain constant. So thank you very much for your patient hearing.
Thank you very much, sir. So there are few questions. Sir, is there any difference between the DCP used in animals and humans?
No. It's the same plate which we are using.
Okay, sir. So thank you, sir. Only a single question being asked by participant. So
Okay.
thank you.
Dr. Raghunath, it was an excellent presentation where you made the basic concepts and applied aspects very clear, and it will help the budding orthopedic surgeon to come out of learning curve very fast. It's really a very lucid presentation, and it will benefit everybody who is interested in orthopedic surgery.
Thank you.
Dr. Tiwari, yeah.
Yes. Thank you, sir. I am very much thankful to Dr. Raghunath, sir, for giving us time, valuable time, for delivering a interesting and wonderful webinar explaining various types of plates and plating procedures in canines that may be very much useful for the participants. I am also thankful to the Dr. Simrat Sagar Singh, sir, President ISVS, Dr. D.B. Patil, sir, Executive Secretary ISVS, for their constant support and motivation. My webinar team, Dr. Nitin, Bhatia, INTAS Animal Health, Dr. Neelesh, Sindhu, and Dr. Divyesh for their constant hard work and cooperation for making these webinar success. I am also extending my sincere thanks to all the participants who have devoted their valuable time for attending this webinar, and definitely this webinar will be helpful for their future endeavors. Thank you each and everyone. Thank you very much.
Wishing happy Diwali to all the attendees and Dr. Raghunath and all the Dr. Tiwari, Divyesh and all the team, Dr. Nitin Bhatia and all, Dr. Neelesh.
Thank you, sir. I thank ISVS and I thank INTAS for giving me this opportunity to share my experiences, sir. Thank you very much.
Thank you.
Thank you, sir.